Hello, everyone. Thank you so much for sticking with us here today at NUGGET 2021. We hope you've enjoyed all the sessions so far. For this last session of the day, we're joined by Dave Lemphers, who will be covering predictive performance with machine learning and real-time telemetry. If you joined us at NUGGET 2020 last year, you may remember Dave, who joined us out of Melbourne, Australia, when he was with AWS. And Dave has actually recently joined the Netrio team, and we're excited to have him. So with that, all systems are go. Dave, take it away.
Hi, everyone, and welcome to my NUGGET 2021 session, Predictive Performance with Machine Learning and Telemetry. Let's get started with a quick intro. My name is Dave Lemphers. I'm currently CTO in residence at Techstars and a technical advisor at Netrio. I've worked on some really fun projects at places like AWS and Microsoft, but also have had the opportunity to be a founder and inventor, focusing on telemetry and AI. When most of us hear the term telemetry, we picture NASA's mission control operators staring at a screen that are tracking a spaceflight, processing incoming data, and making adjustments to ensure the flight follows its trajectory, the intended path or green path. It's all happening in near real time, being produced by numerous onboard sensor systems, being visualized across every screen in the operations center. And while these images are sometimes dramatized by Hollywood, for the most part, telemetry in real life does mimic art. I've spent the last 20 years working on telematic systems, both as a hardware engineer and data scientist. In today's session, I want to take you on a quick trip down my memory lane, discuss my personal journey with telemetry, the different eras from regression to deep learning, and what telemetry means to me when I think about contemporary observability. I will also introduce some ideas around how telemetry, together with forecasting, can change the way we think about systems management and the role of leading over lagging indicators. But to get started, I want to give you some personal stories and experiences of my time working in telematics. When I graduated university, my major was embedded telemetry. In school, it was studied in a very abstract way, broken down into different constituent parts, taught in fragments, and sometimes at levels that were very hard to understand without practical examples or experience. It wasn't until I made it out to industry, working on fuel systems, that the role of telemetry and its input into control systems made sense. After 2 years working in fuel system telemetry, I decided to build my own startup, creating telemetry boards for a range of fuel applications, most notably for the Australian Army's helicopters and for a production racing team. The term telemetry in those fields, especially in embedded systems, is almost always associated with some form of control system. It's because telemetry itself holds little value as an artifact. It's the management actions the operator takes because of the telemetry that makes it valuable. Fast forward to 2008, and I had the opportunity to join the Windows Azure engineering team when it was only known as Project Red Dog, to focus on how we instrumented the data center. We regularly deployed thousands of servers a month into data centers across the globe, each server wired up to the top of rack switch, each rack wired up to the aggregation switches, and then up to core routing. Monitoring a server requires a lot of data. Monitoring a rack of them, even more. Once you get above tens of racks of data, it's not feasible to stare at monitoring dashboards anymore. You need to start using more sophisticated methods to only look at the stuff that matters and ignore the stuff that doesn't. Fast forward to 2015, and I'm working in my third startup, where we're using machine learning and computer vision to predict changes in water chemicals in pools to ensure optimal water quality. Telematics is all about collecting data, but the way you do it isn't always through a linear sensor. We were trialing visual cards that could be deployed in the field, sending color information to a machine learning model trained to detect potential changes in water chemistry. Direct and indirect telemetry was becoming commonplace, and feeding that into forecast models was changing the way we thought about predictions, specifically failure models. Fast forward to 2017, and I'm back at Microsoft, this time as a principal applied scientist. And I'm working on the telemetry backbone that pulls data on how software engineers interact with VS Code. The goal was to try and build a recommendation algorithm to anticipate what an engineer was trying to accomplish in their first few keystrokes, to support accelerating their productivity. I took this approach into my last startup, CodePilot, where we instrumented the VS Code IDE backend, Monaco, with a set of deep learning models that would help hiring managers predict if a software engineering candidate had the potential to become a top developer. I'll wrap up the trip down memory lane for now, other than to say, when I started looking into ML ops, observability, and the domain of monitoring and operations, I was surprised to find the term telemetry used so broadly. I come from a fairly strict definition of the term telemetry, and while I accept it now means a number of things in the monitoring and operations domain, I think there's an opportunity to consider it in more classic terms, but with a new twist, which is what I'm going to cover in the next half of this presentation. And that's what role telemetry plays in the modern systems landscape together with machine learning and data science to help create forecast models, to anticipate potential performance deviations in distributed systems, and provide insight to operators on the actions that can be taken to achieve the green path. Telematic systems architecturally are quite simple. You have the system being observed. This produces data across a time series. The data is transmitted to a receiver, generally somewhere remote, where the data is then processed. Where things get more complex is in two main areas. The first, producing the data in the most efficient yet complete way. The second, processing that data such that it can be effectively influence management operations. Telematic data is often thought about as a frame, where each frame represents the parameters of a system state, the value of the system state, and a timestamp. For example, if I have a sensor that measures the acoustic levels of a pool pump or the keystrokes of a programmer writing code, I can't simply send the decibel level or keystroke rate as an isolated value. I have to accompany it with some description of the parameters too, and I have to do that on some time series interval. With time series intervals, we have to do our best to capture data at the smallest possible interval. Otherwise, we risk what we call the blink effect, the situation where an event occurs in the window between our recording intervals. Much like the blink of an eye, what's the point of recording terabytes of data only to find the event you were looking for happen in between your recording intervals? This is why sampling or polling are such terrible approaches to source data capture in performance systems. We poll or sample because technically it's easier to implement, which means we're optimizing for the engineer developing the telemetry system, not the operator who needs to observe the system. So solving the blink effect is crucial to creating signal-complete telematic systems. Once data is received by the observation system, it needs to be processed towards some goal. In the early systems I worked on, we would model the optimal state of the system by creating a basic linear model. And as telematic data was received, we would construct a new model based on the telematic data, then compare the two models, looking for a score for how much the two models differed, measuring the mean error between the telematic model and the expected model. When there were deviations, we would identify the location of the deviation and signal to the operator that the mean error had exceeded the allowed threshold, with basic information about how much deviation had occurred. In practice, for example, with a race car, the payload operators would be seeing the expected fuel consumption curve, the observed fuel consumption curve, and the point in time where it deviated, together with recorded values for the dependent systems such as the fuel pump and engine RPM sensors. They could then draw hypotheses about what was happening, such as the driver accelerating more than expected at a point in the track, and relay instructions to the driver to change their attack approach to ensure they didn't waste fuel. We can see during this interaction that there is a lot of correlation happening and a ton of domain knowledge that resides with the operators to analyze and interpret the signal data against a model of the system and its environment, and create a remediation plan in real time for how to get the observed model back in line with the planned model. So given the challenges we face with capturing the right amount of data at the source, transmitting it to the receiver, then processing it to identify potential error values between what we expect and what we're observing, what are some of the emerging methods that can be used to address these challenges? And how do they factor into what the future of observability and telemetry look like? Well, before I dig into that, let me do a quick flashback again for the second piece of my personal experience in this space. Back in 2008, Microsoft was experiencing a number of transformations. The first was to cloud. We had been a socket shop for so long, and the thought of selling consumption-based services, shrink-wrapped product was disruptive. At the same time, Microsoft Research, or MSR as it's also known, was investing heavily in how to help Bing produce better recommendations for information discovery. At the time, the world was deterministic. The most advanced ranking and recommendations were happening in SQL and if-then else statements. The challenges to solve were how to scale these approaches as the data got massive. MSR was directing a lot of resources into machine learning and trying to influence engineering leaders to start thinking non-deterministically and towards a probabilistic mindset. The challenge was, how do you take 30 years of engineering where really great code practiced immutability and where your functions took an input and returned an output, with tests to ensure correctness, and tell them instead the future looked like a function taking in a vector and producing a probability distribution? How do you write a unit test for that? In the data center, we were dealing with similar transformations, from deterministic, heuristical thinking to model-driven probabilistic thinking. Instead of setting alarms on threshold states from our servers and network and doing root cause analysis to understand why a server failed, we were moving to real-time monitoring with intelligent alarms that could anticipate a potential performance issue, what we called an outage or system error, and provide us insight into what was the reason the system thought something bad was going to happen. We moved from a reactive, retrospective approach to monitoring and operations to a proactive, predictive approach, and the metrics that matter, such as availability and downtime, improved dramatically, as did operator fatigue. What I learned through that experience was what stayed with me. And we used to treat unexpected events, such as outages or downtime, as historical. The workflow was something bad happened, we troll the logs, do the root cause analysis, come up with a report to explain what happened, and prepare a plan to ensure it doesn't happen again. Break fix was all we knew. That's because we treated the system as static snapshots. When an unexpected event occurred, we took a photo, looked at what was wrong, tweaked some stuff, then hoped it didn't happen again. If it did, we would rinse and repeat. The problem was, what we rarely did as engineers was consider the downstream effects of these unexpected events. When a server died on our top-of-rack switch fried, we only considered the impact of the system. Metrics like downtime and outage window were very inward-looking. What we didn't ever correlate and measure was what happens to the business when these unexpected events occur. We never traveled downstream and followed the wreckage. The server goes down, a customer website isn't available, their customer can't access their product, they churn off the service the next month, a customer becomes frustrated and doesn't trust us anymore and moves to another provider, and we lose revenue. Because we didn't measure system performance issues in business terms, we didn't consider the full cost of unexpected events. When we started to trace these issues out of the data center and into our business units, the folks selling and supporting Windows Azure, we quickly realized that doing historical analysis of unexpected events was useless. We had to move to a proactive model where we could anticipate, or at least detect in real time, an unexpected event occurring and take immediate actions to mitigate or reduce the impact of that event. This created a need for more advanced real-time monitoring of our systems, more intelligent support systems to help us rapidly identify root causes, and most importantly, models that help us detect deviations from what we expected the system to be doing. So back to the here and now. It's 2021, and concepts like open telemetry, observability, and AIOps are front of mind. But what do these really mean? And how much is just smoke and mirrors, or how much is pseudo AI, where SQL and if-then else statements are being dressed up to look like AI? Well, honestly, a lot. The reality is there are very few systems available today that provide very wide, real-time telemetry planes feeding into continuous machine learning models that produce actionable insights to mitigate unexpected system events. It's not impossible, it's just really hard. So why is it so hard, and how can we build these systems today? The first is we have to approach the problem as a whole of machine learning problem. From source capture to transmission to processing to modeling, the whole end-to-end life cycle of telemetry needs to be rebuilt using machine learning. I'll give you an example to illustrate my point. If you're running an e-commerce website with thousands of concurrent users running shopping sessions, clicking on different parts of the website, pulling data about different products from the database, lots of checkout transactions being run. If your goal is to detect a single issue for a single customer, your website application would need to be pushing massive amounts of data from every active user session in real time, with the ability to detect a potential issue and notify a customer success operator before the customer becomes frustrated and abandons their shopping cart. Today, the best case is an engineer might get a system alert in the form of a 400 or 500 family error code, do some log splunking, possibly not find anything because it was an intermittent error, and close the alert. Meanwhile, your customers who were about to spend hundreds of dollars have now bounced because the search page kept timing out. Reimagining this situation, though, your website is running a lightweight, highly intelligent embedded agent. Your engineers didn't have to hand instrument anything. The agent deeply integrates into your technology stack and is recording metrics in real time at high velocity. These frames are being passed through a client-side machine learning algorithm that is analyzing each frame and performing a technique we call singular value decomposition, which learns relationships within the telemetry data, dramatically reducing the size of the data sent, but also sending updates to the underlying machine learning model in the form of its learned coefficients. Or let's imagine that frames are now arriving at the receiving end of the multiple systems, such as your API servers and database servers. And for the system to identify an issue across these system boundaries, it needs some correlation identifier, which of course isn't in the frame data. Using a technique called semantic joining, we can train a model to cluster records based on their semantic similarity and join them using the confidence threshold. Finally, now that we are efficiently capturing massive amounts of data in real time, stitching the distributed records together into a single semantic record and storing that in a time series structure such as an interval map, we can now train a machine learning model to create a projected state for a holistic system view and detect any time a set of telemetry data arrives that is outside of a set of acceptable bounds. What's more, when we detect that deviation, we can also point where the system chain of distributed systems contributed to that potential or forecasted deviation. This information can be sent immediately to a customer service operator with live site information about the customer who is about to experience the issue so they can intercept and remediate before the issue becomes a loss event. This scenario isn't pie in the sky either. All of these techniques are practiced today, albeit within very large cloud providers, to predict performance issues before they occur and remediate them on the fly. This results in tangible benefits to the business in terms of non-IT metrics, such as customer churn or revenue loss. The role of telemetry and machine learning in modern observability is growing, largely due to performance requirements of business owners looking to move away from reactive measures driven by lagging indicators and towards proactive actions driven by predictive performance alerts. The future of observability, therefore, will fundamentally change from answering the question, what happened, to actioning the prompt, this is about to happen. Thank you very much.